Hello, and welcome once again to Clinical Optics Made Easy. I am your narrator, M.N. Wiggins, and we are now going to do the second part of astigmatism, where we talk more about the treatment of astigmatism. And in today's talk, we're going to talk a little bit about time travel, spherical equivalence, axis versus meridian, eggs Benedict, and we're going to talk about another classification system. Once again, I'd like to thank Davis Street Publishing for having me in their studios today, and everything that I'm going to talk about is in that book right there, and if that's the one that you want, you can go to davisstreetpublishing.com or scan that code, but it's in lots of optics books. An important thing is always to work lots of problems. So in our last talk, we talked about the pathology of astigmatism, and now we're going to shift gears. We're going to talk to another part of your brain where it's going to house the treatment of astigmatism so that these concepts are clear for you. A fun way to learn about the treatment of astigmatism is to go back in time. And so that's what we're going to do here. We're now back in time where nothing has yet been invented, including apparently color photography. But in this time period, we have the ability to invent anything that we would like to. So now that we're back in time, our first patient comes in the past, and they tell you that they have blurry vision at distance, but they can see up close. And so you have a clue there that they are myopic. They have a far point in between the eye and infinity. And so what are you going to do? Hopefully your next step is going to be to invent the tape measure, because you want to know how far away is their far point. And if you're smarter than me, and odds are that you are, you likely invented not the one in English units seen here that's 30 years old, but one that's in the metric system to make life easier. And so you invent the metric tape measure and you measure them out and you find out that their far point is 33 centimeters away. And knowing that they have a far point at 33 centimeters, you know to divide that into 100 and find out they are a -3 myope. So now, to create a treatment for this patient, all you need is a minus lens, preferably -3 lens, which has not yet been invented. So let's get right on that. Here we go. We've now invented the -3 diopter lens. And so you take that thing and you hold it up in front of the patient, and they're very happy. They can see, but it's not great. And you're feeling, hey man, I just made this whole lens for you and you're still not happy? But then you start thinking, why aren't they completely happy? Then you remember that this is an astigmatism lecture. And so you start thinking, maybe there's astigmatism. What's the next thing we're going to invent? It's going to be the keratometer. And so you invent the keratometer and you get these readings, and you were right. They do have astigmatism. And you can see that they are steeper vertically than they are horizontally. And so you remember your football lying down, and you know that this is now with the rule astigmatism. So we have -3 diopters that we figured with the tape measure, and we have the 2 diopters that we figured out with the keratometer. Now the question is, how are we going to treat it? What are we going to do about this? Well, here's a key concept in the treatment of astigmatism. So using this patient, we have 42 diopters and we have 44 diopters, and the point or the key to treating astigmatism is getting those 2 focal points together. Because remember, in astigmatism, when we showed you that conoid of Sturm, you had 2 lines that were separated. And what we're really trying to do is put those 2 lines together so that it acts like a spherical cornea. So we're trying to replicate a spherical cornea with an aspherical cornea or an astigmatic cornea. And there are 1 of 2 ways that you can do that. So if I have part of my cornea focusing at 2.38 centimeters and part of it focusing at 2.27 centimeters, I can either add 2 diopters to the 42 so that they both become 44 and they both focus at 2.27 centimeters, or I could subtract from the 44 and make them both 42. In other words, those 2 rays would come together at 2.38 centimeters. And that is how we treat astigmatism. And whether you are adding to the weaker one or subtracting from the stronger one, that is the difference between plus and minus cylinder. It's achieving the same goal, but it's achieving that goal at 2 different locations, whichever cyl that you're working in. So you invent the cylinder to do this. You couldn't use another spherical lens, because if you were -3 and you put another -1 or another -2 diopters, then it'd just be -5, and that wouldn't get you anywhere near what you wanted. You needed to change just one meridian. And so you needed a new kind of lens, a special kind of lens that has curvature just going one way. So let's take a look at what you've invented here. So you can see this looks like a cylinder that's been cut in half lengthwise, and so it's standing up. The power of this cylinder is acting horizontally. That's where the curvature is. If we were a jogger on this cylinder and we were to jog perpendicular to it, it would be a tough jog because we'd be going up and we'd reach the peak and then we'd be going back down. If we were to jog vertically, it would be pretty easy because you can see that's flat. There is zero curvature there, meaning zero power. So all of the power in this cylinder, which is what we wanted, is horizontal. So I'd like to solidify this in your mind, and so we're going to do a little experiment here. I want you to take a sheet of paper that you can see, sort of like the one I have right here, and I want you to hold it in both of your hands so that your hands are under the page. And so the sheet is going to represent light rays, and your hands are going to represent the cylinder power. And then I want you to slowly fold your hands together so that the paper edges roll up together. And what you're going to see is that they'll come together as a straight line. And this is exactly what a cylinder does to light rays. And so as you're holding it right there, you can see the curved parts, and that's where all the power is. And then the 90 degrees away from that, there is no curvature. That is zero power. Okay, so we've invented the -3, we've invented a cylinder, and we put those things together, and the patient said, it's great, but you know what, it's not perfect, and you're really getting frustrated now because you're spending a lot of time, a lot of chair time on this patient. It seems like nothing makes them happy. That's okay. We're going to keep working. You find out that if you just change that -3 to a -4 sphere with that +2 cylinder that you've invented, it's just perfect. And so we're very excited now. And the patient, they're going to talk all about you and they're going to market for you. And that's great because there's no internet right now. You haven't invented that yet. And your business is going to boom. So, but there's a problem. You know that the cylinder must be oriented correctly to fully work because you want your patient to be happy because they're going to be out there talking about you and you don't want them talking bad. So as these glasses are built, and by the way, you just invented glasses, the cylinder is put onto the sphere, they're ground together, but the optician has to get that cylinder in the correct orientation. So you need to communicate with them what that orientation needs to be. And so you need to figure up some sort of communication system. And so you decide that if the cylinder is standing vertically, such as in the diagram on the far left here, that we are going to call that an axis. And so an axis is going to kind of be this dotted line that's going up and down where there's no power on that cylinder in that diagram on the far left. We know that all the power is working horizontally, but the axis is going to be vertical. That's just what you chose, so if you don't like that, I mean, you're the one to blame. So axis here is vertical, zero power. The power of a cylinder is always going to be perpendicular to where we set that axis. The axis is nothing but a label. It's a mechanism for you to tell the optician how not to screw up the glasses. So here it is. We have a -4 sil. We decided to go with a +2 instead of a -2, and that's important, as we'll talk about in lens transposition. But in this case, right now, +2 is what we want. And axis, or X, 090. Again, there's no power at 090. As you can see, that's very flat. The power is 90 degrees away. It's at 180, which is exactly where our K reading said that we needed it. So I'd like you to repeat after me, and if there are other people around, just kind of please do this in your head so that nobody looks at you. Meridians are lines on the cornea where the pathology is. We talked about that in our last lecture. It's going from one limbus through the center of the cornea to the other limbus, and these are lines on that cornea, and that's a pathology thing. Axis, or plural axes, are the labels of how we orient that cylinder in the glasses, and it's just a communication system to the optician. Once again, cylinder power is 90 degrees away from its label. And the cylinder axes are always perpendicular to the meridian of the cornea that they are treating. Let's think about that for just a second. So if I'm using plus cylinder, that means that I want to make the flattest meridian stronger. That's what plus cylinder does. Minus cylinder makes the stronger one weaker, but let's just focus on plus cylinder right now. So I'm going to make the weaker cylinder stronger. So let's say that, for example, my weaker cylinder is 0-180, and I want power 0-180. To get a cylinder with power 0-180, I have to tell the optician to set the axis at 90, because there's no power at 90. The power is 90 degrees away from it at 180. And that's where I want it in that example. So remember when we had to switch back from -3 to -4? What was up with that? That was because of something called spherical equivalent. And here's the formula for that. You take the sphere, you add 1/2 of the cylinder, and that gives you the spherical equivalent. The spherical equivalent for our patient to begin with was -3. But when we added cylinder, we changed things, but we had to keep a value of -3 as we were doing it. And this is going to make more sense as we go along, so bear with me. But this is the formula for it. And it turned out that -4 was what we needed, because our cylinder was 2 diopters, 1/2 of 2 is 1, and a -4 gets us back to the -3 where we started. So once again, you can see here in the bottom in this big messy diagram, we have the conoid of Sturm, and that purple circle there, the circle of least confusion, that is the spherical equivalent. That is our -3. And if we were just going to treat this patient with a sphere only, we would have given them -3, nothing better than that, if we only get to use one lens. But if we get to use 2 lenses, in other words, we can take a sphere and add a cylinder on top of it, which is what we did, a spherocylindrical lens, then we're going to be able to account for those 2 focal lines on either end of the conoid of Sturm, and we're going to bring those 2 focal lines together so that there is no distance between the 2 lines. Because if we can bring those 2 lines together, and that's what we were showing you with the +2 or -2 on that diagram, that is going to give your patient the absolute best vision. And so that's why a spherical cylindrical lens is almost always superior to just a sphere lens alone for people with astigmatism. There are cases where you have to use spherical equivalent, but in most cases you will use a cylinder to treat astigmatism. And that is what we're doing. We're bringing those 2 lines together. I know what you're thinking. Conoid of Sturm is a great idea, but is it anything that I could ever see in real life? Yes, it is, and we're going to show it to you right now. So I've got my tape measure laid out. I've got a light source well away. I've got a lady in blue here figurine, and she is standing at 50 centimeters from that wall. The guy with the guitar is 25 centimeters with the wall. And so I'm going to take my cylinder and check it for appropriateness, and then I'm going to form the conoid of Sturm. So I'm just putting my +2 cylinder here at her position to make sure I get a nice sharp line. And then I've got my +4 cylinder. I'm going to put it at his position, and yep, it looks like a +4. So now I'm going to put these 2 things together 90 degrees apart, just like 2 cylinders would be in regular astigmatism treatment. And then I'm going to show you the conoid of Sturm. And so all the way back here, you can see that first line right there. It's a vertical line. And now we're going to have the circle of least confusion. And as we proceed, we'll get a horizontal line. If I go any further, it's going to get blurred and until I can come backwards, and I'll show it to you one more time. Outstanding. So you can now say that you have seen the conoid of Sturm. Now, why did the line look vertical on the front end? It's because there was horizontal power. Just like that experiment where you folded the piece of paper. When you folded it horizontally, it created a vertical line. Same when we got to his position. If you fold it vertically, it's going to give you a horizontal line. Now, we've been mentioning lens transposition. What does that mean? That is basically just going from +sil to -sil or -sil to +sil. And here's how it works. if I have minus 4 plus 2, 0, 9, 0, and I want that to be in minus CIL, my new sphere is going to be the old sphere plus the cylinder. So minus 4 plus 2 equals minus 2. Next, I'm going to change the sign of the cylinder, so plus to minus. Then I'm going to rotate my axis 90 degrees. So 90 becomes 180. So as you can see here, this becomes minus 2, axis 180. If you're not sure of that, then just work it back the other way. So minus 2, 180. Once again, our sphere, we're adding the cylinder and the sphere together to get minus 4. We change the sign of the CIL, we rotate 90 degrees, and we get back to our original minus 4 plus 2, 90. Now here's an interesting thing. This is Cuban bread, and it's got these poached eggs on it, and then under it is some pork, which is really delicious. And I don't know what you would call these brown things on top of the hollandaise sauce. It's just kind of crunchy fried onion kind of thing. But my gosh, that is an amazing Eggs Benedict. So we've talked about with the rule and against the rule. And it's important to know that there is more than one way to classify our astigmatism. And the first thing we're going to talk about is simple myopic astigmatism. That means that one far point is off at infinity, and one far point is between the eye and infinity. And you're sitting there thinking, well, but myopia, the far point is between the eye and infinity. And that's true for spherical. But remember, in astigmatism, we have two focal points to deal with, always. So here, one is at infinity, one is between the eye and infinity. And it would look like this. So if those rays were coming into the eye, the one coming from infinity, where the far point was, would be perfectly on the fovea. But the other one, because we have astigmatism, would be in front of the retina, somewhere in the vitreous. And that's the one that's going to have a far point between the eye and infinity, as spherical myopia also does. If we did K readings, you can see what they would look like. These are just some examples, maybe 45, 180, maybe 43, 90. And so if you wrote a spherocylindrical lens, if you combine those two, it might look like something such as you see here, Plano minus 2, axis 90. And that's where Plano, Texas got its name, was from this optical principle. That's not true, but you never know. Simple hyperopic astigmatism means that one far point is off at infinity and one far point is back behind the eye. And it would look like this. So you can see here that the one that has the far point at infinity is going to hit perfectly on that retina, and the one that is back behind the eye is, well, back behind the eye. You can see it right there. And so the K readings might look like this, 43 at 180, 41 at 90, and the prescription might look something like you see at the top. What I want you to notice is that although the conoids in both of those two examples are in different locations, they appear to be the same length. Let's check that out. So here are the Ks from the simple myopic on top and the simple hyperopic on the bottom. And if I ask what is the length of the conoid, and so I convert those into centimeters and I look at the difference, they are the same. And you'll notice that they are both 2 diopters of astigmatism. One just happens to be myopic astigmatism, the other is hyperopic astigmatism. So we're going to start really thinking about conoids here. So we talked about it a little bit earlier, but what happens to that conoid when we apply treatment? I mean, what really happens? So we're going to go back to our simple hyperopic astigmatism here. And when we're talking conoid of Sturm, once again, we're talking about the distance between that red vertical line right there on the back of the eye and the horizontal line that's back behind the eye. So that distance is the conoid of Sturm. And the farther apart those two lines are, the more blurriness your patient has. And so we really want to get those two lines together as shown here. Because if I can get those two lines together, then I've fully treated their astigmatism and they're going to see so much better. So the take-home message is that the more astigmatism you have, the longer that conoid is, the more blurry your patient is, and we're trying to reduce it down to 0. Now, here is a very useful concept that we've already touched upon, and that is spherical equivalent versus a spherocylindrical lens. So in the top diagram in the middle, this is simple myopic astigmatism. In other words, one ray is perfectly on the fovea, the other ray is somewhere in the vitreous, but there's a distance between them. And this patient is experiencing blurry vision. However, if I were to give them, say, a -3, as we did in our time travel experiment, that would put the spherical equivalent halfway in between those two lines, and that is the diagram on the bottom right. You see that circle of least confusion is sitting perfectly on the retina. So it's halfway in between those two lines, perfectly on the retina, and they did say that their vision got better. It wasn't perfect, but it got quite a bit better. Now, bottom diagram on the left is me using a spherocylindrical lens, a sphere and a cyl, and that is collapsing that conoid perfectly onto the fovea, and that gives the absolute best vision. So the big take-home point is to understand that when we put a sphere in front of an eye, we are not collapsing the conoid, we are just shifting it one way or the other, depending upon if we're using plus or minus lenses. So in our example with time travel, we happen to use that -3, and that diverged those rays, shifting the conoid back such that the circle of least confusion was put perfectly on the retina. And that did make them better, but it didn't make them perfect. We didn't get perfect until we collapsed that conoid by adding in cyl to make a spherocylindrical lens. Now, we talked about simple myopic astigmatism, meaning that one point was perfectly on the fovea and one point was not. But what if both points were not on the fovea? That would really compound the matter, and we would then call it compound myopic astigmatism. So as you can see here, the vertical red ray and the horizontal, is that a blue? Kind of blue? Blue ray. They are not together. So that is the conoid that has not yet been collapsed. It's causing blurry vision. Neither line falls on the retina. So that is compound myopic astigmatism. Definitely not simple. And so the prescription you can see up there in the corner might look like that to correct that. So let's say this is indeed the power that this eye needs. And what I'm showing you right here is I haven't added the full thing yet. All I've added is that -1 spherical lens. And I haven't added any cyl just yet. So by adding that -1, I have shifted that conoid backwards onto the retina. Remember, before I added that -1 sphere, the whole conoid was in the middle of the vitreous. So now, by using the divergence of a -1 lens, I have shifted it backwards. So now I've at least got one line on the retina, right? I mean, baby steps. It's kind of now this simple myopic astigmatism thing. And so now, if I add in a -1 cylinder on top of my -1 sphere, I'm going to take that red ray and push it towards the retina without moving the blue ray, because remember, the cylinders only act in one meridian of pathology. So that is how a cylinder added on top of a sphere is going to collapse the conoid without moving the blue ray and give them the best vision possible. So again, we talked about the difference between plus and minus cylinder, whether we were adding to the weak or subtracting from the strong. But what we're really doing is we're collapsing that conoid, and we can either collapse it from the front going back like we just did, or if that conoid was entirely back behind the eye, we could collapse it more to the left. Let me show you that. So here we have the same eye, but instead of working in minus cylinder, we're now going to work in plus cylinder. So remember, when we were working in the minus cylinder, we used a -1 to push that conoid back. But now we're going to use -2, and what does -2 do? It pushes it back further to the right. So now we've taken that conoid that we had on the inside of the eye, we've pushed it entirely to the fovea and behind the eye. We've shifted it all the way to the right. Now, when we add that plus cylinder, plus lenses cause convergence. They bring the focal point back to the left. That is only going to work on your blue ray, and that's going to bring it up to where the red ray is. So that's what plus cylinder does. It collapses it back towards the lens or in the direction of the cornea, versus a minus cylinder where you have the conoid on the inside and then you're diverging that red ray so that you're pushing the red ray towards the fovea. And that's the real difference in plus and minus cylinder, is which way you're collapsing. So we talked all about compound myopic astigmatism. There is, of course, compound hyperopic astigmatism where both far points are back behind the eye, and that looks like this. So how are we going to treat that? It's the same way. We're going to take a sphere and we're going to put one of those lines on the fovea. And if we just put the red line on the fovea, then we have the blue line is still back behind the eye, so we would have to use plus cylinder to bring that blue line still towards the cornea or up to the retina. Same thing. Now, if we wanted to use minus cyl, we would have to bring this entire conoid inside of the eye, and then the minus cyl would work on the red line, pushing it to the fovea where the blue line was sitting because of the sphere. And if none of that made any sense to you, here's another way of looking at it. What we have here is a representation of the eye. The blue box hanging in the air there, that is the conoid of Sturm. It is along the yellow string there, which is the visual axis. You can see that we have the lens on one side off to the left. You can see the retina outlined in black there on the bottom. And so that represents the back of the eye. So here we have an example of simple myopic astigmatism. One part of that conoid is right there on the retina. The other part is in the vitreous. Now, if we slide it a little to the left, then the entire conoid is inside of the eye. No part of it is on the retina. So this represents compound myopic astigmatism. If I move the conoid over here, where one part of it is on the retina, the other part is back behind the eye, that is simple hyperopic astigmatism. And if I move it entirely to the back here, that represents compound hyperopic astigmatism. So now we're back to our example of compound myopic astigmatism. So if I want to treat this eye, I have to decide if I'm going to use plus or minus cylinder. Let's say that I want to use minus cylinder. The first thing I'm going to do is put a minus spherical lens on here, and I'm going to push this conoid back to the retina so that I can at least get one line on the retina and half my work is done. So if I'm going to use minus cyl, I want that conoid to be partly still inside the eye, but the other part on the retina. So I'm going to do this. So you can see right here, I've got that conoid right where I want. And at this point, I apply my minus cyl so that I get the front leftmost part of that box to move towards the other end of the box. Now, the other end of the box won't move because the sphere is holding it right there. But the cylinder, which only acts in one meridian, is going to take that meridian and it's going to collapse it so that they come together on the retina. That's if I'm using minus cyl. But here we go again. This is before I treat. Let's say that I want to use plus cyl. What am I going to do? I need that conoid entirely behind the eye if I want to use plus cylinder. So here we go. I'm going to use a minus sphere lens to laterally shift it until the entire thing is back behind the retina so that it's like this. So here we are. Now I've shifted it with my sphere. Now I'm going to add my cylinder to collapse the conoid back towards the retina. So the left end of the box that's on the retina isn't going to move. I'm now working on the right end of the box, of the blue box there, and I'm going to collapse those together. That, again, is the difference of using plus cylinder versus minus cylinder. They all get to the same spot, which is a collapsed conoid on the retina, but they do it in different ways. So I hope that that diagram helps solidify it in your mind if the other diagrams didn't. We also need to talk about mixed astigmatism. That's the case where we have one far point that's between the eye and infinity and the other far point is back behind the eye, and it would look like this. So you can see that right there. The red ray is clearly inside the eye and the blue ray is back behind the eye. If we were to look at this with our other diagrams, this is what it would look like. That conoid is straddling the retina, and that's called mixed astigmatism. And so how do you treat that? It's the same idea. You're going to take some sphere and you're going to move that conoid laterally until one end of the box is on the retina. And depending upon which way you go about it, depends upon whether or not you're going to use minus sil to collapse it back towards the retina or plus sil to collapse it back towards the cornea so that both of those lines come together when they're sitting right on that fovea. So here is once again a diagram of the pathology. This is where compound myopia is versus simple myopia, and then you see simple compound hyperopia and mixed. So we've covered a lot of ground on astigmatism, but there's still more out there. In the remaining part of Chapter 2 in that book, it talks about how to tell astigmatism based upon the manifest refraction. There's also a section on how to combine two cylinders together and get a spherical equivalent. And then, more importantly, clinically relevant, it talks about how to differentiate astigmatism coming from the cornea and coming from the lens. So I encourage you to read that or read, again, the optics book of your choice. And next time on Clinical Optics Made Easy, should you choose to join us once again, we're going to start talking about accommodation, one of my favorite chapters. So thank you for spending a good 31 minutes with me today, and I hope this was helpful. Have a good day.